một bắt đầu. Hello everyone, my name is Fo, and today I'll be presenting a lecture on port digitalization and small port with a focus on two case studies, the port of Rotterdam in Europe and the port of Melbourne in Australia. This topic ties directly into our cost emphasis on the strategic role of port in global supply chains and how modern technology are reshaping maritime logistics. Traditionally, ports have served as physical gateway where cargo is transferred between sea and land. However, in recent years, ports have become far more than logistical node. Rapid globalization, increasing trade volumes, and growing pressure to improve efficiencies and sustainability have driven ports to adopt digital technology. As a result, many ports are transforming into small ports that support real-time operation, data-driven decision-making, and predictive planning. In this lecture, I will first define what port digitalization means and explain why it has become so important in global supply chains. I will then describe the key technology that underpins small port system. Following this, I will examine real-world examples from the Port of Rotterdam, one of the most advanced digital ports globally, as well as the Australian ports that are adopting digitalization in ways that reflect regional logistic needs. Finally, I will discuss current challenges and future direction for small ports as they continue to evolve within the context of global trade. To begin, it is important to clearly define what we mean by port digitalization and small port. So, what is port digitalization? Port digitalization and small port concepts are at the forefront of contemporary maritime logistic research. According to Belmont Carey, Audi, and Forget 2023, small ports are evolving from traditional port system toward digitally integrated ecosystem that leverage advanced technology to support operation, sustainability, and stakeholder collaboration across the global supply chains. Although there is no single universally accepted definition, researchers generally describe a small port as a seaport that integrate digital technology, such as the Internet of Things called IoT, artificial intelligence, which called AI, big data analytics, and automation to enable real-time decision support, optimize resource use, and improve performance across multiple dimensions. These dimensions include operational efficiency, environmental performance, energy use, safety, and security. In simpler terms, ports are no longer just physical spaces, they are increasingly becoming data-driven systems. Importantly, small ports extend beyond the digitalization of individual processes. Instead, they aim to create an interconnected ecosystem of stakeholders where digital platforms enable real-time information sharing among port authority, terminal operator, shipping lines, logistic provider, and regulatory agency. In this sense, a small port is not only about adopting new technology, but about how digital data flow reshape collaboration, coordination, and governance within port environment. A helpful way to think about a small port is as a digital nervous system where information flows continuously between stakeholders, allowing the port to sense changes and respond quickly and intelligently. The evolution of ports is often described in terms of hub of regeneration. While early ports focused on basic cargo handling, the current fifth generation of ports emphasize digitalization, automation, and integration with global logistic network. These developments support resilience, sustainability, and competitiveness in fast-moving trade environments. In summary, port digitalization refers to the comprehensive integration of digital technology to transform traditional port into intelligent, adaptive logistical hubs that support modern supply chains. With this concept established, we can now examine why small ports matter. Understanding port digitalization is closely linked to understanding its importance not only for individual ports but for global supply chain as a whole. Small ports play a critical role in improving operational efficiency. Digital systems collect and analyze real-time data on cargo flows, vessel movements, and equipment performance. This enables port authority to make informed, predictive decisions rather than reacting to disruption after they occur. For example, AI-based systems can forecast peak demand and optimize berth allocation, reducing vessel waiting times. This efficiency gain extend well beyond the port gate. At the supply chain level, more efficient ports help reduce overall lead times and logistics costs. Improved coordination between vessel, terminal, trucks, and rail systems supports smoother cargo flows and enhanced supply chain predictability. This becomes especially important during periods of disruption, such as labor shortage, extreme weather events, or suddenly shift in trade pattern. Small ports also contribute significantly to sustainability. Digital energy management systems allow ports to monitor emission, optimize cranes and equipment power use, and implement shore power solutions for dock vessels. As a result, port can reduce fuel consumption, lower emission, and comply more effectively with environmental regulation. Beyond efficiency and sustainability, port digitalization has important strategic implications. Ports that demonstrate reliability, transparency, and adaptability become more attractive to shipping lines and logistic providers. This enhances competitiveness, increases throughput volumes, and strengthens the economic role of ports within their region. Finally, small ports support integration into wider intermodal transport network. Digital platform link maritime operation with the road and rail system, improving end-to-end visibility and reducing congestion. In summary, small port matter because they improve efficiency, support sustainability, enhance coordination, and strengthen global supply chain resilience. The development of small port is commonly explained through the broader academic concept of Industry 4.0, which refers to the fourth industrial revolution characterized by automation, real-time data flows, and interconnected systems. Research positions small port development as part of this global shift toward digitally integrated infrastructure and operations. Under Industry 4.0, traditional processes are reconfigured using technologies such as IoT sensor, cloud computing, AI algorithm, and digital twin system. These technology integrate data across previously isolated systems, enabling dynamic planning and real-time decision-making. In maritime logistics, this transformation turns port into cyber-physical system where digital intelligence is embedded throughout the physical environment. When Industry 4.0 principles apply specifically to ports, scholars describe this transformation as Port 4.0. Port 4.0 emphasizes both horizontal integration within port operation and vertical integration across the wider supply chains. This means that data flow seamlessly between terminal, port authority, shipping lines, and custom agency and inland transport network. Within this framework, digital technologies support not only operational efficiency but also strategic planning, risk management, and sustainability outcomes. For example, the analytic system can model energy use and emissions, allowing operational decisions to align with environmental objectives. It is important to note that port digitalization also requires organizational and governance change. Successful small ports invest in digital infrastructure, data governance, and workforce skills to ensure that technological capability translate into real performance improvements. In summary, the Port 4.0 framework explains how digital technology transforms ports into intelligent, interconnected nodes within global supply chains. With this theoretical foundation in place, we can now examine the core technology that enables small port in practice. At the heart of digitalization are several advanced technologies that enable automated, data-driven, and coordinated operations. These technologies address long-standing port challenges such as congestion, fragmented information flows, and operational delay by connecting devices, systems, and stakeholders through digital platforms. Internet of Things (IoT) play a foundational role in smart port. IoT refers to network interconnected sensors and devices that collect data across the port environment. In practice, IoT sensors monitoring container location, track equipment condition, record weather data, and measure environmental indicators such as air quality. This provides port with real-time visibility into operation and infrastructure performance. For example, small boiler and quiet wall monitoring system at the Port of Rotterdam demonstrate how IoT supports safety and maintenance planning. While IoT generates data, artificial intelligence and big data analytics transform that data into actionable insights. AI systems use machine learning algorithms to analyze large data sets and support predictive decision making. In smart port, AI can forecast cargo demand, estimate vessel arrival time, and anticipate equipment failure before they occur. This allows port operators to allocate resources more efficiently and reduce disruption. A particular important technology within Port 4.0 is a digital twin. Digital twin are virtual representation of physical port systems that are continually updated using real-time data. In port environment, digital twins can model infrastructure, vessel traffic, and cargo flow, allowing operators to test scenarios and identify bottlenecks before they affect real operation. A useful way to think about a digital twin is as a flight simulator for a port, enabling safe experimentation and informed planning. Other enabling technology include blockchain, which supports safe, secure, and transparent data sharing for documentation and transaction automation and robotics, such as autonomous vehicle and robotic cranes. Collectively, this technology forms the technological backbone of smart port. To understand how these technology work together in practice, we now turn to real-world case studies. The Port of Rotterdam in the Netherlands is a global leader in port digitalization and small port development. As Europe's largest port, Rotterdam handles immense cargo volumes and places digital technology at the core of its strategic vision. The Port of Rotterdam Authority has a proactive digital transformation strategy built around three pillars: seamless operation, sustainable performance, and supply chain connectivity. Digitalization improves efficiency, reduce CO2 emissions, shorten vessel turnaround times, and enhance stakeholder collaboration. A key initiative is the digital twin. We integrate data from ship, infrastructure, weather, and traffic to support predictive planning. Manager can stimulate operational scenarios digitally before applying them in the real world. This is central to Port Vision 2030, which aims for increasingly automated and eventually autonomous operations. Rotterdam also uses platforms like PortStream, standardizing real-time information sharing between shipping lines, terminals, and logistic partners. This improves visibility of arrival, berth availability, and schedule, reducing uncertainty and enhancing coordination across maritime and inland transport. As mass Valacte 2, one of the world's most advanced automated terminal, autonomous crane and guided vehicle reduce manual intervention, improve safety, and increase throughput. Digital systems also enable predictive maintenance, lowering downtime and improving asset utilization. Beyond efficiency, Rotterdam digital strategy supports sustainability by optimizing shore power and energy use, reducing emissions, and meeting European environmental standards. Overall, the Port of Rotterdam demonstrates Port 4.0 in action, combining real-time data integration, automation, and cross-stakeholder coordinations. The Port of Melbourne is one of the most digitally advanced ports in the Asia-Pacific region, implementing solutions to improve logistics, landslide connectivity, and sustainability. A major initiative, the Port Rail Transformation Project (PRTP), uses digital twin technology and integrated data flow to enhance rail freight access. These digital twins combine engineering models, real-time data, and logistics systems, allowing stakeholders to collaborate efficiently, reduce design conflicts, and support long-term asset monitoring. Operationally, Melbourne platforms coordinate port terminal, rail operator, and trucking companies, reducing idle time, improving container flow, and minimizing urban congestion. Digitalization also encourages rail use over trucks, lowering emission and supporting sustainability. Overall, the Port of Melbourne demonstrates how Port 4.0 principle can be applied in an urban intermodal context to boost efficiency and integrate regional supply chains. Small port technology faces several challenges: high initial investment in IoT, digital twin, AI, and secure data system can strain mid-size of developing sport, increase connectivity, raise cybersecurity, and data governance risks. As shared platforms involve multiple stakeholders, workforce skill gaps also pose challenges requiring training and organizational adaptation. Interoperability is another concern, as different systems may not simply share data, necessitating common technical standards and collaboration. Regulatory frameworks often lag behind innovation, slowing the deployment of autonomous systems and digital solutions. Despite this barrier, ports that combine strategic technology investment with governance, stakeholder collaboration, and workforce development can successfully achieve sustainable digital transformations. Small port will continue evolving with technology and global trade. Global maritime data networks will enable real-time sharing across port and shipping systems, supporting coordinated arrival, digital documentation, and end-to-end visibility. Automation and robotics, including autonomous vehicle, remote operated crane, and advanced vessel berthing, will expand beyond terminal. Sustainability will remain central with digital systems linked to energy management, emission monitoring, and environmental KPI. AI will enable predictive planning for congestion, equipment failure, and supply chain disruptions. Workforce role will shift toward data analysis, system management, and strategic planning, requiring continuous learning. These trends highlight that small ports are an ongoing transformation rather than a final destination. combining efficiency, resilience, and sustainability. In conclusion, port digitalization is a fundamental transformation integrating IoT, AI, digital twin, and automation to enhance efficiency, sustainability, and supply chain coordination. The Port of Rotterdam demonstrates how a global hub can implement Port 4.0 through real-time data, automation, and platform collaboration. The Australian port like Melbourne show regional adaptation, Melbourne digital twin, and rail integration improve intermodal efficiency. Challenges remain cost, cybersecurity, workforce adaptation, and regulation, but strategic planning, collaboration, and governance can overcome these. Port digitalization is more than a technological upgrade. It is a strategic shift redefining ports as intelligent, adaptive, and resilient nodes in global trade networks. So these are references, and thank you for listening.